Welcome to Unit 5, Analytical Applications of Differentiation. In Lesson 5.1, we're going to be looking at two different versions of the same idea, the mean value theorem and Rolle's theorem. As we'll see, Rolle's theorem is a special application of the mean value theorem. Our standard for this lesson is functions-1.b.1. If a function f is continuous over the open interval ab, and differentiable over the closed interval AB, then the mean value theorem guarantees a point within that open interval where the instantaneous rate of change equals the average rate of change over the interval. Our instructional objective for this lesson is students will be able to apply the mean value theorem over an interval in order to justify conclusions about functions. Our inquiry question is, how can we use existence theorems to draw conclusions about a function's behavior on an interval without precisely locating that behavior? And this lesson is aligned with Topic 5.1 from the 2019 course and exam description of College Board's AP Calculus AB curriculum. Let's look at the next few examples. We've got the first two of 4 graphed functions and a set of 6 directions that we're going to go through. The first one says draw the secant lines for each figure on the given intervals. So looking at the first graph, we can see that our interval here is denoted by the 2 vertical dashed lines, and the intersection of those lines with our graph y equals f of x. And so a secant line is going to pass through both of those 2 intersections, the endpoints of our interval. So if we line up our straight edge, then we can hopefully sketch a secant line that will pass through those 2 points, and we'll come off to the side. Alright, now let's take a look at the next part. It says, are there any points on the graph of each function where the tangent line to the graph appears to be parallel to the secant line you've drawn? Draw tangent lines between the endpoints of the given interval if possible. Let this point of tangency be called x equals c for each figure. Okay, so let's go back. So remember, a secant line crosses the graph at more than one point, but a tangent line just touches the graph at only one point. So, you know, I could actually, looks like maybe here I could have a tangent line. Maybe down here have a tangent line. Now, these digital tools are nice because I can translate this all over the screen and it's not going to rotate. But if you're doing this on paper, it's very easy to lose the angle that you have. And so what I would encourage you to do is use your grid paper and good old-fashioned Algebra 1 to find the slope of your secant line and then use that same slope to construct your tangent lines. So here's how we'll do that. I'm going to look for a corner where the grid lines intersect each other, and I'm going to try to find one of those corners that is on my secant line. And actually it looks like there's one right here. And so starting at that point, if I go down 1 and then I go over 4, we can see that we have a slope for our secant line that is equal to -1/4. And so all you would need to do then would be to line up your ruler on your paper so that you have a line passing through those same types of corners where you have one corner and then you go down 1 over 4 and there's another corner, and then just simply try to orient it in such a way that it's touching the graph. And so doing that here, we get one possible tangent line, and I'll color this one blue. And then we have another possible tangent line right here. I'll color that one orange. Okay, so then we have another point of tangency about right there. And so using C, we can call this C1, and I would say that's approximately 2.5. And then down here for second tangent line, this is just a little bit past 7, maybe even a fifth of the way over. So let's call that C2 is approximately 7.2, 7 1/5. All right, so let's look at number 3. So for each figure, estimate the value x equals c where this occurs, or explain why it's not possible. Okay, well, so for number 1, that's going to be C1 approximately 2.5 and C2 approximately 7.2. Let's take a look at the second figure. Okay, let's look at figure 2. So again, we have an interval, which in this case is going to be from 2 to 7, indicated by our vertical dashed lines and these points of intersection. And so sketching the secant line through these 2 points over the interval, let's see, there we are, and here our interval points actually pass through corners on our grid line, so it's pretty easy for us to see the slope here would be, let's see, we're going to rise 1, so we rise 1 and we run 1, 2, 3, 4, 5, and so that gives us m is equal to 1/5. Now, what about drawing a tangent line on this interval that is parallel to our secant line? Well, so if we go anywhere on this curve, we're going to have curves like this. You know, at this point on the curve, we could have a line like that that's a tangent, and then it's this cusp right here, because at that cusp, the tangent line is actually vertical. It's a vertical tangent line. And so I'm like, well, okay, everything on the left part of this piecewise function is out. What about the right side? So again, we start trying to construct various tangent lines, and I mean, we can, with not much effort at all, convince ourselves that, yeah, there are an infinite number of tangent lines that I can draw, but not a single one of them, in this case, would have a slope parallel. In fact, all of them will intersect our secant line. So let's see. So for number 2, we can say this one's not possible. They want an explanation, and so we can just say that, well, you know, we have a cusp. Now let's look at figure 3. Now figure 3 is interesting because it's not a continuous function. We have a discontinuity, a jump discontinuity located at x equals 5, and so the indicated interval here is from 5 to 10. So, and that's going to be an open interval because 5 is not included. So I need a closed interval, and so the closed interval would be not the whole, it would be this point right here. So it's interesting. We've got these piecewise defined function, and I'm looking at this interval from 5 to 10, and if I look at the open interval, it's one thing, but if I look at the closed interval, it's something else, but the closed interval is what we're talking about. So I am actually going to use the endpoint from our first piecewise defined function and one of the points on the curve of the second piecewise function to construct this. So what I'm going to do, let's see if we can line up those 2 points. I think that looks okay. Alright, so we've got a secant line that passes through those 2 points. So the question is, can I construct a tangent line to the curve parallel to the secant line? So keeping our slope the same, I think we can do that. And it looks like our point of tangency is going to be at x equals 6. So let's call this C approximately 6. Now, just kind of for investigation, let's say that we also consider the interval 1 to 5, and we looked at this part of the curve over here. So let me just sketch a vertical dashed line over here, and so we would have this point of intersection right here. So let's draw the secant line. So here is another secant line, And the question is, could I construct a tangent line that is parallel to that one? So let's see if we can do that. Let's call this one C1. Since it's on the left side, we'll say that's approximately 3. And this will be C2, approximately 6. The slope of this tangent line is going to be -1/2. And the slope of our red tangent line is going to be 2/5. So let's go back and answer these questions. So for number 3, C1 is approximately 3 and C2 is approximately 6. And let's look at our last one. Here we have another piecewise function, and again it's one that has a cusp, which would mean a vertical tangent line. However, notice that the interval indicated here is from 1 to 5. And so on that closed interval, let's sketch our secant line. Alright, so there's a secant line. Not perfect, but okay. Let's see if we can sketch a tangent line. So here's our tangent line, and approximately x equals 4 would be our point of tangency. So we can say that C is approximately 4. And again, our slope for both the secant and the tangent line is going to be n equals -3/2. So 4, we have C approximately. Alright, so let's do a little bit of analysis now and think about what's going on here. Which functions are continuous on the intervals? Figure 1 is, figure 2 is, figure 3 is not, figure 4 is. So if we name the functions, that's f of x, g of x, and k of x. So f of x, g of x, k of x. Which functions are differentiable on the given intervals? Well, for figure 1, this function is going to be everywhere differentiable. So there is no place on this curve where we can't construct a tangent line. Now, in figure 2, we ran into a problem because at the cusp, the function is not differentiable because the tangent line is a vertical line, meaning that the slope is undefined. Or, in other words, since the slope is equal to the derivative, that's a way of saying the derivative does not exist. Figure 3 is not continuous, so if it's not continuous, it absolutely cannot be differentiable on the interval. However, on the interval, if we redefine the interval from 5 to 10, that portion of the function was continuous and differentiable, and from here 1 to 5, this portion of the function was also continuous and differentiable. So if we just kind of cut out the discontinuity, we can still make some application of our investigation. Likewise, in figure 4, this function on the interval is going to be continuous and differentiable, but the overall function itself again has a cusp, which would have a derivative that is undefined. So let's just go and talk about some of these continuity issues and differentiability issues. So which functions are differentiable on the given intervals? So f of x, k of x, which are not differentiable. Explain why. Well, okay, g of x has a cusp. H of x is not continuous at x equals 5. Alright, okay, so the mean value theorem says if f is continuous on the closed interval, that's the interval that contains the endpoints, so you can't have a hole as an endpoint, and if it is differentiable on the open interval, so not necessarily including the endpoints, then there exists a number c that is an x value on that open interval from A to B, such that f prime of c, what is f prime of c? It's the slope of the tangent line, is equal to f of b minus f of a over b minus a. What is this? It's the average rate of change. It is the difference in the y values of the secant line divided by the difference in the x values of the secant line. And so this is an idea that we have informally seen many times before, but we're formalizing it now, and this is an example of what's called an existence theorem. So this allows us to prove the existence of C, even if we don't know exactly where it's located. We know that it exists. So a way of kind of restating this verbally, we're saying that the instantaneous rate of change, slope of the tangent line, is equal to the average rate of change, slope of the secant line. Graphically, the tangent line is parallel to the secant line. Now, I mentioned earlier that Rolle's theorem is just a special case of the mean value theorem. Let's take a look at Rolle's theorem. It says let f be continuous on the closed interval AB and differentiable on the open interval AB. So this is the same condition that we had to meet for the mean value theorem. So that's the same. Here's where Rolle's theorem is a little different. It says if f of a is equal to f of b. What does that mean? Well, it means that at the point x equals a, you have a given y value, f of a. And they're saying that at the point b, you have a y value, f of b. They're saying that those two y values are the same. Now, what does that mean? It means the slope of the secant line is going to be 0, because f of b minus f of a is equal to 0. So they say there exists at least one number where f prime of c is equal to 0. In other words, there has to be a tangent line with a slope of 0 on that same interval from a to b. So the conclusion of that is that if these conditions hold true, there is at least, there could be more, but at least one number between a and b so that the tangent line is horizontal. And so that's what we have here. Here, f of b, let me just say it this way. So here we have f of b for b. We have f of a corresponding to a. And over here, the y value, we have f of b. So what we're saying is that at c, we have f prime of c is going to be equal to 0. So again, a and b are going to be the endpoints of the interval. And once again, this is an existence theorem. And so all we're doing is proving the existence of an x value c that is on this interval such that the slope of the tangent line at that x value is equal to 0 or horizontal. So here we can draw our tangent line that is horizontal. So we've talked a little bit about how Rolle's theorem and the mean value theorem are similar. In fact, Rolle's theorem is a special case of the mean value theorem, but let's talk about their differences. So what is the difference in conditions between the mean value theorem and Rolle's theorem? Well, Rolle's theorem has a secant whose slope is 0. What does Rolle's theorem tell you must exist on a given interval? So an extrema. Now, it goes without saying, but maybe I should say it anyway. It's a local extrema because it's on an interval. So a local extrema, that can be a max or must exist. How do we know that it's a max or a min? Because those are the points that have horizontal tangent lines or slopes of 0. That's an important idea. That's something we're going to come back later when we look at something called the first derivative rule. Alright, in example 1, they tell us to use the table of values below to sketch the differentiable continuous function on the grid. So we have a t-table, values of x, and the y value, which is given by the function g of x. I'm just going to plot these ordered pairs. So at 0, we have the point 1. At 2, we have the point 4. At 4, we have the point 8. 6, we have 12. 7, we have 13. 9, we have 11. 11, we have 9. Sorry, at 11, we have 8. 13, we have 6. 15, we're back to 8. 17, 14. And so we know that it is continuous and differentiable, and so we'll just try to sketch a smooth curve through this. Alright, so we have something that is pretty close to a good function here. Alright, so let's see what we need to do. Find the average rate of change of g of x on the interval from 2 to 9. That's a closed interval, so we are going to identify the end points on the function. So here is 2, 4 and 9, 11. So we have the point 2, 4, and we have the point 9, 11. So our average rate of change is going to be the slope of that secant line. So it is f of 9 minus f of 2 over 9 minus 2, which is 11 minus 4 over 7, and that's going to be equal to 1. Is g prime of 6 equal to the slope of the secant line? Well, let's take a look at 6. So at 6, let's see, I would say that it's not parallel, but we can give an argument for that. So this seems to have a slope that is approximately 3/2, and the slope of the secant line is 1. So this has a slope that's approximately 1.5. Alright, so using 6, 12 and 4, 9, g prime of 6 is approximately 12 minus 9 over 6 minus 4, which is 3/2, which is not equal to 1. Let's look at part C. Does Rolle's theorem apply in the interval 4, 9? Explain why or why not. So on the interval from 4 to 9, Rolle's theorem would not apply, and the reason is f of 4 is not equal to f of 9. So we can say no, because f of 4 not equal to f of 9. So therefore f of 9 minus f of 4 over 9 minus 4 is non-zero. And at part D they ask, is there another interval where Rolle's theorem applies and provide some justification for that. Oh, we really just need to find two y values on the function that are the same. And so y is equal to 11 at 4 and 9. So we can say, yes, Rolle's theorem can be applied on the following intervals. Four less than or equal to x less than or equal to 11. And 11 and 15 both have a common y value of 8. Then less than or equal to x less than or equal to 15. And we can furthermore say that in both intervals the slope of the secant line is 0. And we can show that pretty easily. So there we have a slope of 0, and here we also have a slope of 0. And what's more, g is both continuous and differentiable. In example 4, they tell us to let f of x be equal to 5 minus 4 over x. Find all values of c in the open interval from 1 to 4 guaranteed by the mean value theorem. So the first thing we want to do is mark off our interval. So let's go ahead and sketch a secant line through those points for 4. Okay, so here's our secant line. So let's begin with the slope from our secant line. F of 4 minus f of 1 over 4 minus 1 is equal to the, so this is average rate of change. This is going to be equal to the instantaneous rate of change for some unknown value c. Well, the instantaneous rate of change is given by f prime of x. So if we take the derivative of this function, this is 5 minus 4x to the negative 2. Okay, let's take a look at example 4. Here we have f of x equals 5 minus 4 over x. Find all values of c in the open interval from 1 to 4 guaranteed by the mean value theorem. So if we look at points on our function for those endpoints, we have 1, 1, and 4, 4. If we sketch a secant line through those two, this is going to be the line whose slope will be equal to the slope of the tangent line. So let's see what we can find. We're going to begin with average rate of change. F of 4 minus of 1 divided by 4 minus 1 is equal to, so average rate of change is equal to the instantaneous rate of change. That's going to be the derivative of this function. Well, this is 5 minus 4x to the negative 1. If we take the derivative, the 5 goes away. Negative 1 times negative is positive 4 over x squared, or 4x to the negative 2. So we get 4 over x squared as our derivative. That's going to be the slope of the tangent line. So we have 4 minus 1 over 4 minus 1 is equal to 1 is equal to 4 over x squared. So multiplying through by x squared, we get x squared equals 4 and x equals plus or minus 2. Well, negative 2 is not on the interval, so c equals 2 satisfies the mean value theorem on the open interval 1 less than x less than 4. And in fact, if we go to the x value of 2, alright, so there's our tangent line at x equals 2. So the mean value theorem allows us to identify exactly where graphs rise or fall. Functions with positive derivatives are increasing functions. Functions with negative derivatives are decreasing functions. Let's look at example 5. In example 5, they say find all values between the x-intercepts for which Rolle's theorem holds for the roots of f of x equals 4x squared minus x to the 4th. Verify with your calculator. Okay, well, so first of all, this is a polynomial, and so I can argue that f of x is continuous and differentiable everywhere. Now, you can graph this function on your graphing calculator, and it's going to look something kind of like this. So we got to find these roots. So we'll do that next. When f of x is equal to 0, we get negative x squared times x squared minus 4 equals 0. Which gives us x equals 0, 2, and negative 2. And you can find that on your calculator also. So here's 2, 0, and negative 2. Alright, so next, we'll take the derivative and find our instantaneous rate of change. F prime of x is equal to, by the power rule, 8x minus 4x cubed. And then factoring, we get negative 4x times x squared minus 2 equals 0. Solving, we get x equals 0. Positive square root of 2, negative square root of 2. Now these are what we call critical numbers, and they're the values for which the slope is equal to, the slope of the tangent line is equal to 0. So at 0, positive square root of 2 and negative square root of 2, our function has tangent lines with a slope of 0. So let's write that conclusion up. So for the interval negative 2 less than x less than 2, Rolle's theorem applies for x equals negative square root of 2, x equals 0, and x equals positive square root of 2. So in example 6, they tell us to determine whether g of x equals sine 2x plus 2x satisfies the hypothesis of the means value theorem on the interval from 0 to pi. If so, find all numbers c in the open interval a to b such that g of b minus g of a equals g prime of c times b minus a. Okay, notice this is nothing more than g of b minus g of a over b minus a equals g prime of c. All they've done is just multiply through the equation by b minus a. So the first thing that we want to do is to make an argument about differentiability and continuity. So let's do that. So 1, our composite function is comprised of a sine and a polynomial. Well, okay, fine. Sine and polynomials are everywhere continuous and differentiate 2. Let's plug in our endpoints 0 and pi. So sine of 0 is going to be 0. 2 times 0 is 0. So that means that g of 0 is equal to 0. And if we plug in pi, we get sine of 2 pi plus 2 pi. Sine of 2 pi is 0. 0 plus 2 pi is 2 pi. So g of pi equals 2 pi. Now we're going to need g prime of x, so let's do that. So g prime of x is going to be, by the chain rule, 2 times cosine 2x plus, and the derivative of 2x is just 2. And then we have g of pi minus g of 0 over pi minus 0 is equal to g prime of x. So that means 2 pi minus 0 over pi minus 0 is equal to 2 cosine 2x plus 1 in parentheses. And so 2 pi minus 0 over pi minus 0 is 2 pi over pi. The pi's cancel. We get 2 equals 2 cosine 2x plus 1. We get cosine 2x plus 1 equals 1 when we divide both sides by 2. Sorry, I don't need parentheses there. It's just cosine of 2x plus 1 equals 1. And subtracting 1 from both sides, we get cosine 2x equals 0. And solving that equation gives us 2x equals pi over 2, or 3 pi over 2 from the unit circle. And dividing through by 2, we have x equals pi over 4, 3 pi over 4 on the interval from 0 to pi. And I've not left myself any room here. So therefore, c is equal to pi over 4, comma, 3 pi over 4 on 0 less than or equal to x less than or equal to pi, satisfy the mean theorem. And that's it for lesson 5.1. Thanks for watching, and we'll see you tomorrow. Do the homework for lesson 5.1.